Equally bad choice would be a million. Why? Because you'll take forever building one tree. So there are certain constraints. If you, in the absence of any, if you don't want to think about it, just snap it to the wall. Yes.
And for the last part of the experiment, for the decision tree for that continuous data, can we just try to transform our data to a new space? Like now we have from 1 to 500. And then I say, okay, I will change it. Kind of try to discretize it, like finding the mean of each column or.
Sure, yeah. So yes, you can. So there are. So in the homework, in actual homework that was released, not in the discussion, in the homework, we deliberately did not tell you how to, pick how to discretize. This is a design choice that you have to face when you apply these ideas in the world. So, I think on Canvas, Gianni has posted a link. I don't know if she's here. Okay, Gianni has posted a link about an option for choosing such a discretization. You can try that, or try something else. Come up with a same idea. One, for example, idea which may not work in this data, I think, it depends on how the features are distributed, is to think about splitting at the middle. Splitting at the middle in the absence of any information is probably not a great idea, because what if all your features are clustered outside? So there's some exploration to do, but this is an exploration that you have to do anyway. If you have to, for example, in your projects, many of you are planning to use something like this, the stuff you see in this homework for your competitive project. And interestingly, the features in the competitive project are real valued. You have to face the same decision, make the same choices. So, in some sense, this homework can be seen as practice for your project.
So the link that she posted recommending that we change our ID tree, but can we just instead of changing the ID tree, change it?
The features. You can change the data. Yeah, sure. In fact, that's the example that we saw in the class when we covered decision trees long back, right? We literally just introduced the buckets. We bucketed the features, and then we said, you know what? The features looked like they were continuous, but actually they're not. They're just discrete. And then you just throw it at ID3. Try that.
The last one
is
for in the theory part, there are two questions that are almost similar. Like you ask us to prove that exponential term can be written as a product of two terms, and the question about is proving that term is kernel, which if it's proved that they are almost the same.
Yeah, all the questions in that part are basically going to look very similar. They're going to ask, sometimes the proofs might be because of a sentence that you just wrote.
But if you prove for that, you already proved for the other question. I mean, the same proof. Because if you prove for exponential term in the third question, we prove for the last one, which is just for grad students.
Oh, sure. Yeah, sure. That's right. Yeah.
It's confusing.
You can refer to that proof if you want. Yes.
But I think those are asking slightly different questions because.
Can you remind me what the expression is?
So number 2, you have an exponential expression multiplied by.
So in some sense, that's right. In question number 2, you are asked to explore how kernels interact with each other. If you know that something is a kernel and something else is a kernel, how do you build a bigger kernel, for example?
And that part is straightforward, but for part 3, it's asking show that this is an inner product of infinite dimension.
The Gaussian.
Yeah, the Gaussian.
RBF kernel. Yes.
Right, and so.
How do you do that?
And so I'm looking at it's based on the difference between two vectors.
Yes.
And I'm not sure how to transform the difference into an inner product. That doesn't make
you have
sense
power
to me.
minus of a difference, right?
Yeah.
Okay. Let's the first thing you should try is to think about what is e power minus x. You know it's an infinite sum,
Yes.
right? Okay? It's an infinite sum of what? Of basically monomials. Right? Okay? Examine one of those monomials. Is that an inner product?
Okay.
What if you had some normalization, for example?
But I mean,
Were you able to prove that the polynomial? Oh, I see. So you have the quest. Okay, let me just write down the. We have. Something like this.
yeah.
Right. Now, at the risk of. No, actually, no, I'm not going to give away the answer. So, the question is asking you to prove that this is an inner product in possibly an infinite dimensional, with a possible infinite dimensional transformation.
Yes.
Right? Okay. Now, you know that this is an infinite sum.
That's true, yes.
Okay. You can take one of the terms in the sum. What will that be? Just
It would just be,
one is there, but tell me something that involves x and z. xz?
it would be that expression, like, for example, raise to the power 2 over 2 factorial.
Uh-oh. Something like that.
Yes.
Okay. Now, does the question say anything about the x and z being normalized? Okay, you know what? I'll take this offline.
Okay.
Because this is going to take a little bit longer than I would like to spend right now. So meet me after the class, partly because I want to start today's lecture.
Oh, okay, no problem.
But yes, this is, I will get back to you on this and probably post a message on Canvas right after class.
Okay.
Okay. So those of you who are here, it doesn't matter whether the class is being streamed live or not. So I guess there's no point in making that announcement. Today we're going to start a completely new section of the class on probabilistic learning. So let's just see what we've done so far. Throughout the semester, we've been asking the same question multiple times. What does it mean to learn? And different ways of answering this question gives you different learning algorithms, different ways of quantifying learning, formalizing learning. The first thing that we saw was online learning. Actually, the specific instance of that we saw was mistake-bound learning. And there we said learning is the same as just stopping. An algorithm is a classifier is said to learn if it stops making mistakes. If you bound the number of mistakes, that means then you say that learning is complete. We saw examples of mistake-bound algorithms, perceptron, and we saw theoretical examples like the halving algorithm. And then we moved to pack learnability. Pack is a different way of asking the same question. Does it mean to learn? What does it mean to learn? And the way we answered it was, we defined this whole a formal definition. Learning an algorithm, a concept class is learnable if you have these many examples, for instance, and you define learnable in terms of not exactly getting the answer right, but you're allowing an error of some epsilon. And you're not asking whether the learning algorithm gets the classifier that has error epsilon. You're asking what is the probability that the classifier will get the learning algorithm will get a classifier with a low error. And under this regime, we were able to prove interesting statements about learnability without even looking at the algorithm, just by looking at the concept class. But as a side effect of pack learning, we were able to derive, literally just from a question on a theoretical question on pack learning, we came across an algorithm, the Adabust algorithm. Does weak learnability imply strong learnability? The answer is yes. And the proof is a constructive thing in the form of the Adabust algorithm. And then we saw that we talked about VC dimensions and such things, and that led to the support vector machines. Under each of these definitions, we analyzed various algorithms and we we came up with different ways to ask, how do you find a function that produces a label given an input? Remember, a classifier is just a function. Yes?
Did we discuss how the VC dimension discussion led to these support vector
Yes,
machine?
we did.
Okay.
In fact, we started the support vector machine discussion with VC dimension, with agnostic learning. So, agnostic learning implies, means that it's a good idea to have small VC dimension, and for linear classifiers, larger margin gives you smaller VC dimension, and maximizing the margin is a support vector, gives you support vector machines. Alright, today we're going to, in fact, for pretty much most of the rest of the semester, we're going to come up with, look at what might be considered the third pillar of this kind of formal analysis of machine learning, which is called Bayesian learning. Under this regime, this is like a massive area of machine learning, just like PAC and online learning. So, just to give you a sample of what's going on in this space, we'll be looking at two learning algorithms: the naive Bayes classifier. How many people here have heard of the naive Bayes classifier? A non-trivial number. And logistic regression. I mentioned logistic regression in the last lecture also, and logistic regression is one of those classifiers that is like a bread and butter classifier. It's like support vector machines. If you're not sure what's going on, you should first try something like SVM or logistic regression just to get an idea of what's happening. So let's start the discussion. Today's lecture, we're going to not going to look at any learning algorithms. We're going to look at this principle of Bayesian learning. And in particular, we look at two criteria for finding classifiers called the maximum a posteriori learning and maximum likelihood learning. I'll go through to work out through two examples in class based on the binomial distribution and the normal distribution, and hopefully at the end of the class we'll get to this theoretical idea called the Bayes optimal classifier. Let's get started with Bayesian learning. So I just want to clarify something before we move into Bayesian learning, which is when you talk about probabilistic learning out there in to people who are practitioners of machine learning, often two different concepts get blended. One of them is the idea of learning a probabilistic concept. Okay, what does that mean? So far, we've been looking at hypothesis classes, right? Linear classifiers, for example. Linear classifiers give you a decision. Give it an input and you get a decision about true or false, spam or not spam. One extension to this is, instead of thinking of a single decision made by the classifier, we can ask, what is the probability that the output is true? The classifier does not give you a decision, it gives you a probability of true and false given the input. So the classifier itself does not make the decision, it only gives you the probability. What this means is, in some sense, this is a bigger hypothesis space. So instead of learning functions that we saw earlier, which takes inputs to false or true, we'll be learning functions, I'm just going to call it C, which takes inputs to the range 0 to 1. And you can interpret that as a probability under certain conditions. So these are, you can think of this as probabilistic classifiers. They produce a probability instead of a decision. The nice thing about probabilistic classifiers is it turns out that with some minor tweaks to what we've seen in learning theory, we can analyze such classifiers. But as far as today's lecture is concerned, we're going to talk about Bayesian learning. And in Bayesian learning, we're not going to learn we're not going to talk about probabilistic classifiers, but we're going to talk about a probabilistic criterion for choosing a classifier. You had a question?
Yeah, I just want to go back to learning. It still predicts the output, right? I mean, just knowing the probability is no good.
Oh, sure. That's actually a philosophical discussion, because one could argue that maybe knowing the output is not interesting, it's the probability that's interesting. I'll give you an example of where that might be useful. Suppose we are doing something like active learning, where the learning algorithm goes out to the world and asks questions. What is the label for this example? It has to pick an example where it is most uncertain. How do you know the label is it's most uncertain? You look at the probability. The decision doesn't matter if the probability, for example, is close to half or if the entropy is very high. That means it's most uncertain, and that's the example where it has to solicit a label.
Right, along with probability, won't it say whether it's a positive or negative?
It could, but there are certain applications where just the probability is useful. Where, for example, you want to use not one classifier, but you want to combine two classifiers, and you want to make them agree with each other, and you're willing to change the label of the classifier that's less confident. And there you have to start reasoning about probabilities of these outputs rather than just the decision itself. But good question. That's a useful thing to keep in mind. So in Bayesian learning, we are going to not necessarily worry about whether the classifier is predicting a probability or not. Instead, we are going to use a probabilistic criterion to pick a classifier. Okay? And the classifier itself could be deterministic. It does not have to predict a probability. For example, you can have a Bayesian criterion for picking a decision tree, for instance. Now let's kind of explore this. Excuse me. Let's explore this idea a little bit. Remember, for most of the semester, we've been talking about learning as being the following process. Given a data set, let's call it D, our goal is to find the best hypothesis in a hypothesis space. And the game has been, how do you define best? How did we define best for SVM?
Biggest margin,
The one that has the maximum margin. We could have defined best for SVM in a slightly different way. Instead of thinking of maximum margin, remember we spoke about loss minimization. The best classifier is the one that has the least loss. Equivalent. In Bayesian, in a Bayesian universe, we will define best classifiers as the classifier that's the most probable given the particular data set. In order to make that work, we need to assume a probability distribution, or not assume, somehow we need to build up this idea of a probability distribution over the entire hypothesis space. So you have a hypothesis space, let's just pretend that the hypothesis space is this line, and you somehow have to find some probability distribution. So this is H, and the y-axis here is probability of the hypothesis given the data. So there's more there that I don't have room for. And if you're Bayesian, you might say the best one is this hypothesis here, because you're finding the one that's most probable. Which means we need to construct that function. We need to somehow build the definition, the idea of a probability of a hypothesis given a data set. And we need to understand what's the connection between the data and the hypothesis space. In SVM, the connection between the data and the hypothesis space is through these weights. The hypothesis is entirely defined using the weight, and each point, each example, we are claiming that each example can be classified as a dot product. We need to build up something like that, and that's called the model. The weights are the model. Before getting into the details, Bayesian methods. Since we have not seen Bayesian methods before, I just want to tell you about how it shows up and why it's useful. First of all, like the other algorithms that we saw, Bayesian methods give you practical learning algorithms, the naive Bayes classifier or the logistic regression. But one thing that's actually more a more powerful tool that we have, because if we use Bayesian method, is it gives us a clean framework for introducing and incorporating prior knowledge into our decision making process. We can directly introduce prior knowledge So if you believe that the hypothesis space, the true classifier, suppose you believe that the true classifier is a classifier, let's call it H0. Some hypothesis, some function. Let's say you are convinced that the classifier is H0 for whatever reason. And you see some data. And you know that there is noise in the data collection process. You see some data, and it turns out H0 is not doing as well. There's a different hypothesis, H1, that seems to be doing better on this training set. But for whatever reason, you are convinced that H0 is the true classifier. Okay? How would you incorporate that idea into support vector machines? If you believe that a certain weight vector is the best one, but your data seems to think otherwise, and you know that there's noise in the data, can you incorporate that information in the support vector machine? Yes.
There is something called alike term dot product. In finding a minimum loss, there is something called alike.
Something called what?
When you find a minimum loss,
Right.
there is dot product.
Right.
Maybe there you can.
Yeah, so you can you have to tweak the loss function. Every time you have a different kind of prior knowledge, you have to somehow start from scratch and tweak the loss and do all that. The nice thing about being Bayesian is that it gives you a uniform way of handling this kind of prior information. If you believe that for whatever reason the prior knowledge tells you that H0 is the classifier, but your data tells you that H1 is the classifier, then you're building probability distributions over the hypothesis. So this might also get a somewhat high probability because you've incorporated your prior belief. A Bayesian classification also gives you a framework for reasoning about other learning algorithms. It turns out that you can think of these regularizers. We saw regularizers in SVM, right? Turns out there's a really cool Bayesian way of interpreting regularizers. We'll see that next Tuesday. Anyway, so let's get started. Let's get started with the mechanics of Bayesian learning. We'll start with Bayes' rule or Bayes' theorem. How many people have seen Bayes' theorem before? Excellent. I'm not going to ask how many have not seen it before. So the Bayes' theorem is like it should be something that is in your bones. It's saying, let's say you have events X and Y. Bayes' theorem says the probability of the event Y occurring having observed X, this is called the posterior probability of X, is proportional to the likelihood of X, the posterior probability of Y is proportional to the likelihood, that's the probability of X given Y, times the prior probability of Y. We'll explain this, we'll go through this in a little bit more, but I just want to mention a little notational shortcut that I'm using, and you typically see all over when you read the stuff. When I say P of Y given X, capital letters indicate events, and P of Y given X really means probability that the event Y is taking some Yi, and event X is taking some value Xi. Let's analyze this a little bit. So, let's say that we care about the probability that an event Y has happened, knowing that some other event X has happened. That's what we care about. And what we have at our disposal are the following devices. We have something called the prior probability. Prior probability is our belief that the event Y happens. The probability, for example, that think of Y as let's say it raining. X is it rained and Y is the grass is wet. Let's say the other way around. We observe that the grass is wet, that's X, and Y is what is the probability, we care about knowing the probability that it rained last night. So Y is so we are in this game we are asking what's the probability that it rained last night after we open the window and observe that the grass is wet. And Bayes' theorem says we need to have the prior probability. What's the probability that it rained? Okay, that's P of y. What's our belief that it rains in general, independent of whether the grass is wet or not? And the P of x given y, it's called the likelihood. It's asking, what's the likelihood of observing x if the event y happened? What's the likelihood that the grass would get wet if it rained? In this case, it's probably 100%. And then the posterior probability is what we care about. What's the probability of the event y happening, having made the observation that we care about? And then there is a term that's in the denominator which we will permanently ignore, because we'll see why, because we'll end up maximizing this term and the P of x will go away. So as far as we are concerned for now, what you need to remember, and this is something that you should remember, if I wake you up in the middle of the night, you should be able to tell me what today's rule means. The posterior probability is proportional to the product of the likelihood and the prior. Okay? Because the denominator, for our purposes, you can think of it as a constant. Okay, so before going ahead, are there questions about this? Yes?
So if we were to multiply by probability of x and divide by probability of y, we've just reversed everything. And so now P y given x
Yes.
is a likelihood. So how, do we say that P
Yeah.
x given y is likelihood of x? Or is that likelihood of y?
So P of x given y is the likelihood of x. Is the
Okay.
conditional probability, the class conditional probability, it's also called the class conditional probability if you are being a Bayesian classifier. I'm assuming here that, think of this as there's like an input-output situation. We have some inputs, x, and we care about the state of y. For such situation, all this notation. Other questions? Alright, so just a quick refresher on probability. I expect that all of you have seen this before, maybe in like 3rd grade or something. But just a quick refresher. If you have events A and B, we can ask what is the probability of A and B happening, and we can also write that as P of A comma B, and that's simply the probability of A given B times probability of B, or probability of B given A times probability of A. There's a sum rule. The probability of A or B is probability of A plus probability of B minus probability of A and B. You should understand and know and be comfortable with the idea of independence of events. We have used the idea of independence, conditional independence in the past. Two events are independent if the probability of the two events happening together is simply the product of their individual probabilities. Probability of A and B is probability of A times probability of B. And then if you this is the theorem of total probability, is again something that you hopefully have seen before. If you have many events A1 through A1, that are all mutually exclusive, which means that what does mutually exclusive mean? Mutually exclusive means the event A1 and A2 cannot happen. And let's say the probability of all those things is they add up to 1. For instance, you can have something like, if you have a classifier, every email, we are assuming, can either be spam or not spam. It cannot be both, and it cannot be neither. And which means the probability of spam plus probability of not spam should add up to 1. Though think of those as your A. And the theorem of total probability says for any event B, notice that B is not even necessarily conceptually related to A. For any event B, you can write the probability of B as simply the sum of these terms, the sum of probability of B given AI times probability of AI. This is, we'll apply this trick of marginalization quite often. Not often, but it shows up quite a bit, so you should be comfortable with this. And hopefully all of you, I'm hoping this is not the first time you're seeing this stuff. So please go back and open up 3rd grade textbooks or whatever, wherever they teach probability now. Alright, so now that hopefully the basics are at least back in cache, in your front end at the top of your cache. Let's think of Bayesian learning. The fundamental idea between Bayesian learning is that you treat the choice of a data set and the choice of the classifier themselves as events to which we ascribe probabilities. You are given a data set, right? You're given a data set, let's call it D, and it consists of a bunch of examples. Now, you just happen to have this data set, but that's an event. It's possible that another data set could have been chosen for you. It's possible that, if you sample the instance space again, you'll get a different data set. So the choice of a data set is an event. Either you get that event, does that make sense? The choice of the data set is an event because one can think of a way to generate the data set by just sampling the instance space multiple times. And every time you do the process, you get a different data set. The choice of classifier is also an event because you have a choice. You can pick one classifier in the entire hypothesis space. You choose little h, the classifier h. And these are both events, and we can ask, what is the probability of a classifier h being the true classifier, having observed a particular data set D? That's the posterior probability here. What's the probability that the true classifier is hypothesis H, having observed a data set D? But because we are treating both the choice of the classifier and the selection of the data set as events, we can apply Bayes' rule. So we can apply Bayes' rule, and this is just replacing x and y with D and H here. And to answer the question that you had before, we care about finding a hypothesis. That's why we ask for probability of hypothesis given the data set. So x is like the data set here. And let's analyze what the different parts of the Bayes theorem mean in this context. Suppose we have a prior probability of a hypothesis being the correct one. This is what I mentioned when I said Bayesian learning lets you use background knowledge. Probability of H, the term in blue here, does not really talk about the data set. It's asking what is the probability that the classifier is a particular classifier in the absence of any data set. Even before having seen a single example, what's the probability that a certain classifier is the correct one? We could choose to use this information if we want, or we could just make it uniform. The likelihood here is what is the probability that the data set, there's a mistake here, it should not be data point. Think of this for now as the entire data set. What is the probability that this entire data set was constructed by this classifier H? If H is a true classifier, what is the probability of observing this data set? Yes?
Are we assuming that the hypothesis space is finite?
So the question is, are we assuming that the hypothesis space is finite? Not really. We could have probability distributions over infinite spaces. In fact, we will do that.
Isn't that probability of H can be 0?
Sorry?
Isn't that P of H can be 0?
Oh, yeah, there are some subtleties here. Okay, yes, I see your point, and I'm not going to go there. Yes. So we can ask. Eventually, what we'll end up doing is we'll end up parameterizing these classifiers using, say, a bunch of parameters, say the weight vector. And now instead of P of H, we can say that H is actually has a one-to-one mapping with, say, a weight vector. And now we can ask what is the probability that this weight vector is a true one, so we can put a Gaussian distribution. And this would become the Gaussian, the normal distribution over the vector space. Does that? But yes, you did ask, that is a subtle question. So, anyway, the first term here, the prior probability, is asking what is the probability that a hypothesis, a classifier, is the true classifier without ever seeing a single example. And the likelihood is asking what is the probability that this particular data set was created by a classifier H. And Bayes' theorem tells us the posterior probability, which is what is the probability of that H is the true classifier for this data set. And Bayes' theorem tells us that the posterior is proportional to the product of the likelihood and the prior. Of course, there's a P of D term, which is kind of bizarre, and I'm not sure how to interpret it. It's asking what's the probability of observing this data, and by without any knowledge about the hypothesis, and that requires you to apply the theorem of total probability, marginalize the hypothesis, and it doesn't matter. I mean, we're going to get rid of it very quickly, so let's not worry about it for now. Okay, but before going ahead, do these interpretations make sense of how we are applying Bayes' rule in this context? Yes.
So I'm not very clear on about the box on the right. How do we know whether the hypothesis is good without even knowing what it is?
How do we know?
I mean, what does that mean?
What does that
question mean?
Okay, so interesting question, and this is something that can be a bit of a struggle. Let me give you an example of how we've already done that. Let's take SVMs again. We have the regularizer term, right? So remember let's just, for now, so let's remember. So you have an SVM where you're trying to minimize, and I pick SVM mostly because I feel like, I hope you guys are comfortable with it, and you're, since you've been implementing it in your homework, might be something that loss. There's some loss term, I'm not going to write that up. And the SVM says, let me write this as loss of W. Okay. Now, you know that only the loss term is affected by the data set. Now, suppose the data set size was 0. What would the SVM pick? Which weight vector would it pick?
Whatever you started out with.
I mean, think of the optimization problem. Forget the algorithm. Think of the optimization. If the data set is empty, this whole term disappears. So you are asking what is the minimum value of this quantity? 0. There's your prior. What you're saying is, in the absence of any knowledge, the SVM has a bias towards the 0 weight vector. In SVM, we implicitly had that prior. We never thought of it as a prior, but we did. Why did we do that? Because we had this whole margin story, but we have some prior knowledge, we introduced it. How do you know that the classifier is the true classifier in the absence of any data? Maybe you know something about the domain. Maybe you are a domain expert. Maybe you believe that the class, I don't know what the correct answer is, but I think the answer is somewhere in this region. So it's a way of targeting your search. Remember, learning is search over hypothesis space. A prior is a way of targeting your search over a certain region of the hypothesis space, favoring a certain region. Okay, so at this point, the question is, how do you choose a hypothesis? There are two criteria that show up quite a bit. One of them is called the maximum a posteriori rule. The maximum a posteriori criterion, or the MAP criterion, is simply find the you pick a classifier that has the highest posterior distribution. This is the posterior. The posterior distribution is simply what's the probability of the classifier having observed the data. The maximum a posteriori, like the name seems to suggest, is find the classifier that has the highest posterior distribution. This is a condition that, this is like a standard way of doing Bayesian learning. And we know, we just saw by Bayes' rule, the posterior is simply proportional to the product of, I can just apply Bayes' rule on this thing here, this is by Bayes. And choosing the classifier that has the highest posterior distribution is the same as choosing a classifier that has the highest value of P of D times given H times P of H divided by P of D. Do you have a question? Okay. But notice, and I kept telling you that the denominator is not really relevant, you shouldn't be worrying about the probability of the data, and the reason for that is right here. Notice that in this expression here, only the numerator depends on h. We want to find a classifier that has the highest quantity in this box. Inside that box, only the numerator is dependent on the hypothesis. The denominator does not depend at all on h, which means as far as h is concerned, P of D is a constant. So this is constant. Right? Which means we can just throw that out because we are doing a maximization. If I ask for our max, let's say absolute value of x minus 1, it's exactly the same as our max absolute value of x minus 1 divided by 14. Right? So the denominator is just a constant with respect to the thing that you are maximizing over. So we can get rid of the denominator, and that gives us what is often seen as the standard form for map learning. So let me just to remind you. So the likelihood, we want to find the classifier that's that has the highest posterior probability, and this is exactly the same as finding the classifier that has the highest product of likelihood and prior. This is the standard form in which maximum a posteriori learning is presented. So, does it make sense so far? Any questions?
It's like the in reverse problems, right?
Yeah, it seems bizarre, right?
Yeah.
It seems like this, we want to find, in fact, that's a very good observation, and it's not just a good observation, it's something that everyone notices.
What was the observation?
The observation is, I want to find the probability of hypothesis given data, and it seems like the things that you care about are the thing that you care about is the probability of data given hypothesis. And this tends to throw off people quite a bit. But it's not magic. I mean, it's just an application of Bayes' rule. And in fact, I have seen even people who've used this idea quite a bit in their day-to-day, day-to-day routine. Once you're in the weeds and you're tired with implementing the stuff, suddenly you're like, what am I doing? Am I doing maximizing probability of, why am I doing probability of D given H? And then you have to remind yourself it's the Bayes rule at action. So in order to find a classifier, in order to define this whole process, right now I've just given you a criterion. In order to complete this definition, you still need a way of asking what's the probability of H, or formally writing down what's the probability of H and writing down what's the probability of D given H. But before that, suppose you do not have any prior knowledge. Suppose you don't have any preference, about one hypothesis or the other. In other words, suppose you assume that the probability of H is the same across all hypotheses, because you are letting the data do the entire job, you are not bringing in any prior knowledge, then probability of H disappears in this expression, right? This becomes a constant. If you assume that the prior distribution is a constant, then you can simplify this process by saying the classifier that is produced is simply the one that maximizes the likelihood. Remember, I say likelihood, but the way to think about it is, what is the likelihood that this classifier produced the data set? So, this is called the maximum likelihood estimation, and very often this is the maximum likelihood estimation is the one that's used because sometimes you just don't know. You don't have any prior knowledge, you don't want to introduce any prior knowledge that may damage your classifier, you just pretend that all hypotheses are equal and you just find the one that has the maximum likelihood. So maximum likelihood estimation is another equally common Bayesian criteria. Questions? Oh, next. Yeah.
Is that a good assumption?
Sorry?
Is that a good assumption?
Is that a good assumption? That's a good question. Sometimes yes. Sometimes you don't have any other choice. Sometimes, for example, let's say I just give you some data. I don't tell you anything, and you are not a domain expert. Like the way I've been doing for your homeworks. You have no knowledge. So, in the absence of any knowledge, sometimes it's better not to commit to one of the classifiers. That's right. In practice though, if you're being Bayesian about linear classifiers, it's often a better assumption to introduce something like a regularizer, something that introduces a preference towards smaller hypothesis space. So the prior, if you're Bayesian, the prior is the place where you introduce this Occam's razor kind of a sort of a, what do you call it, preference. That's it. Sometimes we don't have a choice because for some rather complicated probability distributions, it becomes intractable. We just cannot write down this maximization function in a way that we can solve it. So we just throw up our hands and pretend that we don't have any knowledge. So it's a combination of being uninformed and and unable to solve the optimization, which forces us to go to. And sometimes maximum likelihood is so easy to write down, it's very tempting to use. Yes?
So does the last equation just say that go through all the hypotheses in the set and find the data that best suits?
No, you don't find the data that best suits. The data is fixed. You go through all the
Right,
hypotheses in the set.
And see if the data fits that hypothesis.
Exactly.
But isn't that what we're trying to do?
Yes.
So have we just rewritten our requirement and...
Okay, keep thinking about this, you'll get to the answer. So, let's say you have two, I have an example here, but I'll just give you the quick summary. Let's say you have two hypotheses that are competing against each other. The maximum likelihood estimate would be, you take hypothesis 1, you ask what is the probability that this hypothesis generated the data. And which means that we need a functional way of writing down this expression. We haven't done that yet. And then you take hypothesis 2, you ask what's the probability that it generated the data. Whichever one is bigger, you just take that. And by choosing that, we are actually doing maximum a posteriori with a uniform. We don't have any preference over one or two. That's why we are doing maximum likelihood. I'll give you an example that might actually clarify this in a minute. To go back to the question that you had, it's often computationally easier to just do maximum likelihood. And in fact, in practice, another computational trick that is almost, it's the de facto one, is you don't ever typically we don't maximize likelihoods, we maximize log likelihoods. Because it just makes the calculus easier. You'll see that when you see an example. Alright, so to answer your question, at this point, technically, everything is solved. If we had infinite computation, if we are able to do maximizations and minimizations over arbitrary sets, we've solved the problem. If, say you have a hypothesis space capital H, what you do is you iterate through this entire hypothesis space, and for each one of them you calculate the posterior probability of that hypothesis given the data, and then you pick the one that has the highest value. Technically, this problem is solved. I mean, of course, that's a ridiculous algorithm. It's not gonna work for anything but the simplest case. But conceptually, that's what it is. You seem to have a question.
No, I'm just scratching my head.
Okay. Alright, so let's look at some examples to see where this goes. This example I'm going to just give you, I'm going to walk through how to apply maximum likelihood estimation. in order to do that, we need two things. First of all, what we have is that we have defined our rule for identifying the best classifier. And the best classifier in this game is the one that maximizes the likelihood of the data. Of course, we need to instantiate this. We need a hypothesis space, and we've always needed that. And we need a model. The model tells us how could the data set be computed or generated if the hypothesis was a particular one. In other words, we need a functional way of writing down the likelihood function. So let's look at some examples. Say you have done your class and then you decide to become a consultant, a machine learning consultant for a local startup. And this company makes glass beads, and they want to know what's the probability that the beads will break when you drop them from how many feet? 20 feet. And of course, the first question that you ask is, are they identical? Meaning, are they identically distributed? Of course they are. I mean, they have an excellent manufacturing process. The next thing that you do is, you don't know anything about beads. So you need to do an experiment. You need to collect some data. So what you do is you start breaking them. You drop them from, you drop 5 beads from 20 feet, and you see that 3 of them break and 2 don't. And you say, oh, the probability that the beads break from 20 feet, or the probability of failure is 0.6. Why? Why is the probability of failure 0.6?
Mathematical?
What does that mean? That's like saying by magic. How many trials have you done? And how many of them failed?
3.
So 3 out of 5 is 0.6. I know you know the answer and you're pretty sure that that's not the answer. At this point, I'm convinced that you are convinced that it's a trick question. I assure you it's not. But let's try to derive this. I'm going to argue, I'm going to point out that this kind of trivial counting thing that you just did is actually a maximum likelihood estimate. So we have, we have two possibilities here. Either there's failure or there's success. Let's assume the probability of failure is some number p, which means the probability of success is 1 minus p. What you know is that each trial is IID, which means it's independent and identically distributed. The probability that one bead fails is the same as the probability that another bead fails. Okay, so you've seen your data. Let's say you've seen these 5 examples, you have 3 failures and 2 successes. Your data, D, is this set here, or this sequence here. The probability of observing this, now you have got, suppose the true probability of failure was P, then what is the probability that you would have seen this particular observation? The probability that you would have seen this observation with 3 failures and 2 successes is simply P cubed as 1 minus P squared. Why? Because there are 3 failures and 2 successes. This is each of these correspond to a failure and these correspond to successes. Right? So the probability of seeing this particular data set is P cubed 1 minus P squared. Now the maximum likelihood estimate is asking what is the value of P that maximizes this quantity here. So already, this may seem like a very trivial thing, but already we have seen 2 things that, an instantiation of both the aspects of maximum likelihood estimate that we need for maximum likelihood estimation. One of them is we need a hypothesis space. Here the hypothesis space is completely defined by one number, P. The hypothesis space is completely defined by this particular probability. The search for this probability of failure is simply the search over the range 0 to 1, where P can be between 0 and 1. We also need a particular, a way of creating probability of D given H. How do we know? And each D is simply the product of quantity of, let's call it di given h. Di is, maybe it could be one of these things. And so we've written a functional form for the likelihood function. So this is exactly the likelihood function. So maximum likelihood estimation is asking, what is the probability, what's the value of p that maximizes this quantity q? Before going ahead, are there questions? What do you do next? I want to find p. I want to find a p that maximizes this quantity. How do you do it? You could do that, exactly. So at this point, it's a calculus problem. It turns, so I care about that, but it turns out that it's actually easier if you maximize the log likelihood. In general, if you have A successes and B failures, I can write the likelihood as p power b 1 minus p power a, because little p, remember, is probability of break. And at this point, it's just an exercise in Calc 1. You can take the derivative of this quantity, set it to 0, and you get the probability of the maximum likelihood estimate is simply b divided by a plus b. What is that? It's the number of failures divided by the number of failures plus the number of successes. The probability of failure, and we had here in the example that I had, you had 2 failures and 3 successes. So maximum likelihood estimate is exactly what your intuition told you it was. It's 3 divided by 5. So, yes?
Is there any mathematical proof behind that, or just someone came up with logics?
Which one?
That is not finding maximum for...
I just proved it to you. How did I prove it? I assume, so first of all, I assume, and this is important, I made an assumption that the maximum likelihood is what I care about. This is our, in some sense, search criterion. Under the search criterion, the bias of this coin, or anything that you want to think about it, is the number of, the count of what you care about divided by the total number of tries.
Right, but on the previous slide we had another equation that said it's better to find the log of that. So it's just an assumption again.
No, it's just a trick. So I want to find max of p times or r max. Let's say I want to find r max of some function of x, right? But it's the same if f of x is a function that only produces a positive number. This is the same as r max log of x. Why? Because log is an increasing function. I could replace it with any increasing function. It just so happens that this particular mathematical trick is convenient for this functional form, because I can say then log, this whole thing is simply log p times b plus a times log 1 minus p. And I want to take the derivative of this with respect to p. It's easy. On the other hand, if I could have done it on the original thing, you just end up with this mess of a equation to solve. Okay, so what we assumed here is that we have a binomial distribution, that the probability of break is a single number p. It turns out you can also parameterize this in other ways. Maybe you can write down this probability as some function of the bead itself. Maybe you can have features from the bead. You can ask what is the diameter, what's its density, and those could be features. You could write down a linear classifier or a logistic model. You can make other model assumptions. What I just proved is under the assumption that this is a binomial distribution. Let's look at one more example. And this is actually pretty cool because this gives you a connection between maximum likelihood estimation and least squares regression. Remember we saw least squares regression? Like way back. What seems like a century back now. I'm going to show you that least squares regression is exactly the same as a maximum likelihood estimate for a particular model assumption. Let's start this game. Suppose, so we care about regression, which means we need to predict real valued outputs. So the input, let's say, is some feature vector x, and the output is a real number. And we want to search over all functions that can take these kinds of feature vectors, these points in d-dimensional spaces, to real numbers. So the x's are vectors and the y's are real numbers. And let's just blindly apply what we saw with maximum likelihood. But before that, we need to make assumptions. Again, we need to somehow come up with a way that connects these inputs and outputs. And this is also, you will also hear the phrase the generative story. The generative story is the way in which the data is generated, given your modeling assumptions. In this case, we are going to make the following generative story. What you do is, we assume that input, the points x's are labeled in the following way. The data set is created in the following way. A random point is chosen. A point x is chosen in this d-dimensional space. And there is this true hidden oracle function f that is not shown to us, and that function is applied to this point, xi. And then at that point, if nature were kind, it would just give you the label. But nature is slightly annoying. So what it does is, instead of just giving you the value of the function, it perturbs it slightly by some noise. It adds some noise, let's call it ei, to this value. So just to repeat, you pick a random point, xi, and this point is chosen arbitrarily from some instant space, the vector, d-dimensional vector space, and this true function, the hidden function, the oracle function, is applied to this point, and then before giving the label to us, before telling us that this xi has the label f of xi, a certain noise is added to that label. And we assume that nature, for whatever reason, chooses to apply a noise that's drawn randomly from a Gaussian distribution. So you pick a certain, let's say this is the space of y. If this was f of y, the probability that the observed label for this example would look something, if I was a better artist, you've seen Gaussian distribution. With some probability, it would probably tell us that the label yi is this thing, and this difference is ei. And this process is repeated m times to generate the training data. So what I have just told you is the generative story. How is the data set created? I haven't told you anything about what we have made, what the function f looks like. Now, suppose we have a hypothesis. Suppose we want again, the thing that we need to worry about is how good is a particular hypothesis under this generative story. Suppose we have a hypothesis, we want to know what is the probability that a particular label, actually this is a real valued label. What is the probability that a particular label was generated according to this story? And according to the story, the error for this label is y minus h of xi, right? If h was equal to f, remember that y is f of x plus some error. if the true function f is the hypothesis that we have at hand, then the error for this particular hypothesis would be y minus h of x. And under our generative story, we believe that this particular value of error is from a Gaussian distribution that has zero mean and fixed, and this is important, a fixed variance sigma. Which means we can ask, what is the probability of observing this particular data point? Probability of observing this particular data point comes from the Gaussian distribution, right? Because the error is Gaussian. Okay. If the true function were of the function h, then the probability of the data point xi, yi was observed is this expression here. That's for one data point. We have m examples and they are all independent. So we can ask, what is the probability that your entire data set was generated by this function h? Since they are all independent, it's simply the product of this expression over the entire data set. Questions before we go ahead? I haven't told you anything about why this looks like least square, and that's the fun bit that comes up. Okay. Now, notice that what have I done so far? I have not made any assumptions about what this hypothesis space H looks like, but I have come up with a story that I believe generates the data, and under this generative story, under this generative model, I'm able to write down the likelihood function. This is exactly the likelihood function. Yes.
What is the middle symbol? The partial infinity?
This one?
Yes.
Proportional.
Proportional.
Yes. Other questions? So we've been able to write down the likelihood function. What do we do next? Say you are given the data set, you can write down the likelihood function, maximize it.
The log maximum.
Exactly. So our goal is to find the most likely hypothesis. In other words, the maximum likelihood estimate. So we maximize the likelihood. We are able to write down the likelihood as this expression here, and this looks rather hideous. But if you take log, and you've already heard the answer, you can take the logarithm, you can simplify it. This looks rather hideous, but then it becomes rather simple. So let's just look at the little pieces. So if you take log, the product becomes a sum, and this part is simply the same as the log of this part, which is a constant, because we are assuming that sigma is a constant. And then the thing on the exponent shows up right there. So maximizing the likelihood under the assumption that the error is noise is the same as maximizing this quantity here, but maximizing the negative of a quantity is the same as minimizing the quantity. Now is this cool or what?
Yeah.
Now we started off with this god-awful expression on top, but with this rather elaborate story of how the data was generated, and we've come to something that looks awfully familiar. This is let's analyze this. The most likely hypothesis is the hypothesis that minimizes the sum of the squared errors. If the function h, we've not made any assumptions about h so far. If the function h were a linear regressor, in other words, function h simply is defined entirely by a weight vector w that takes your input x and produces the output as the dot product, the maximum likelihood estimate is exactly the same as the one that minimizes the squared error under this, the maximum likelihood estimate under this assumption. So we made an assumption about how the data is generated. Under this assumption, the maximum likelihood estimate is exactly the same as the squared error. So, questions before we go ahead? Let me, so it turns out this is actually the probabilistic explanation for the least squares regression method that we saw. And it turns out that you can analyze not just linear regression but many learning algorithms from two wildly different perspectives. From the loss minimization point of view, for example, we write down a loss. What's the loss? The loss is just some quantity that we want to, that's a penalty that's paid for misclassification or misprediction. In this case, the loss is the square loss, the difference between y and the prediction square. The way I introduced linear regression at the earlier part of the semester was to say it is a loss minimization problem. Every mistake made by the classifier is penalized, and penalized how much? It's the square of the difference of the true label and the predicted value. And you add up all the penalties and you find the weight vector that minimizes this total penalty. This is your least squares regression. On the other hand, if you were a Bayesian, the Bayesian perspective would be, oh, there's no such thing called penalties. What we have done is we believe, for whatever reason, that the errors are generated from the normal distribution with a zero mean and a fixed variance. And what we have done is, under this assumption, we have applied the maximum likelihood principle and we get this estimate. Turns out they are identical. I mean, they are mathematically identical. But how you came to this expression might actually dictate how you interpret the value of these outputs. And maybe the other interesting thing is, sometimes it might be easier to come up with these learning, construct these kinds of objectives if you are in one of these two camps. And so it's worth understanding both these camps. Some people tend to be quite aggressive about their choice of which camp they fit in. Personally, I don't. I'll take whatever works. So are there any questions about this? So there's a minute left, and I'm not going to get into the Bayes optimal classifier, even though it should only take 5 minutes. So let me just quickly start winding up and summarizing what we saw today. We started this discussion on a completely new way of defining what does it mean to learn. If you are Bayesian, the way to think about it is learning a classifier is the same as finding a classifier that maximizes the posterior probability. That's the maximum a posteriori estimate. If you did not know what the prior distribution over hypothesis were, then you might want to relax it to a maximum likelihood estimate. And both of these are extremely popular. And we will see in the next class, we'll see naive Bayes classification, and I'll derive the maximum likelihood estimate for naive Bayes. And in the lecture after that, we will see the logistic regression classifier, and I'll derive both the maximum a posteriori and the maximum likelihood estimate for logistic regression. And that will also lead to this really cool integration between loss minimization that we saw in the last lecture and the maximum a posteriori estimate for logistic regression. We saw two examples, and I encourage you to go back and work out the examples. I've said this multiple times. The best way to learn math is not by watching somebody do it. So you should go back and explicitly work out the details just to convince yourself that I'm not lying. Alright, so let's stop now. There's a homework due today, so please get that done. And I've changed the schedule a little bit. I promised homework 6 will be released today, but I noticed there's a gap towards the end of the semester, so we've shifted the schedule a little bit. Take a look at it. Alright. I have office hours now if you're interested.